Assalamu alaikum. Hope you're doing fine. You might have observed when a freely suspended magnet is disturbed, it shows rotatory motion. This rotatory motion of the magnet is due to the torque experienced by the magnet in the presence of a magnetic field. We know the magnetic field which is acting on this bar magnet is nothing but Earth's magnetic field. And the magnetic field of Earth is a non-uniform magnetic field. But in a small region, it acts as uniform magnetic field. Whenever a magnet is placed in a uniform magnetic field, it experiences a torque. As a result, it starts rotating. In this video, we are going to discuss about torque experienced by a magnet in the presence of uniform magnetic field. To get the expression for torque acting on a bar magnet placed in uniform magnetic field, I consider a uniform magnetic field. We know a magnetic field in which magnetic field lines are parallel are referred as uniform magnetic field. Here, what I have drawn is nothing but a uniform magnetic field, as magnetic field lines are parallel to each other. Now, this arrow mark represents the direction of magnetic field. This magnetic field is denoted by letter B vector. When the magnetic field is acting in this direction, means this side we have north pole and here we have south pole of the magnet which has produced this uniform magnetic field. Okay, now here in this uniform magnetic field, a bar magnet is placed this way. This bar magnet is inclined at an angle theta. With respect to the magnetic field. Okay, then we know every magnet have got the two poles. This is the north pole of the magnet and this is the south pole of this magnet. And I take one point here at the center. I denote this point by letter O. I call this point as midpoint of the bar magnet. Then the distance of this magnet between the poles is considered as 2L. The length of the magnet is 2L. If it is so, the distance between O and L will be small l. Similarly, the distance between O and S is nothing but L again. Alright. Now, I find the perpendicular distance between north pole and the south pole of this bar magnet. For that, I drop a line from here and I do the same thing from this point as well. These two lines intersect at this point. Now, the length of this line provides us the perpendicular distance between north pole and the south pole of the magnet. Okay, it is unknown. Let me find out the value. Yeah. Now, if you look at this carefully, let me join this too. If you look at this carefully, you find it is nothing but a right angled triangle. Right angled triangle. I draw this right angled triangle here. This is the angle theta. You know, the side which is opposite to the angle is referred as opposite side. This is the adjacent side. And this one is the hypotenuse. Hypotenuse, okay. And from the diagram, the length of hypotenuse is nothing but 2L. It is 2L. Clear? And the length of opposite side is unknown. This is what I am going to find out, which provides us perpendicular distance. Okay. In case of a right angled triangle, sin theta is equal to opposite side divided by hypotenuse. Clear? From the diagram, the length of hypotenuse, when your hypotenuse side is 2L, will be opposite side, this side sin theta. Now, if we cross multiply, we get the value of opposite side. This 2L sin theta. Clear? I box this. So, the length of opposite side is nothing but 2L sin theta, that I write here. The 2L sin theta. Okay, then let's see what happened when the magnet is placed in uniform magnetic field. Here, the north pole is getting attracted towards the south pole of the magnet, which has produced this uniform magnetic field. So, this experiences a force which acts in this direction. Attractive force. I name this force as F n vector, as it is experienced by north pole. Then south pole is getting attracted towards the north pole of the magnet, which has produced this uniform magnetic field. Okay, and this acts in this direction. Okay, and I name this force as F s vector. It acts in this direction, opposite to Fn vector. Here, the force Fn vector acts in the direction of uniform magnetic field, whereas Fs vector acts in the opposite direction of uniform magnetic field. It is obvious from the diagram. Now, these two forces constitute a couple. In physics, when we say couple, it means two forces which are equal and opposite. Equal in magnitude but acting in opposite direction on an object. Here, two equal and opposite forces acting on an object is referred as couple. So, it constitutes a couple. Now, we know the force acting on a magnet is obtained if we multiply magnetic field with the magnetic pole strength. Here, the magnetic pole strength of a north pole of this magnet is Qm, and the pole strength of south pole of the magnet is also Qm. Then the force Fs vector is also obtained if you multiply magnetic field with the pole strength, magnetic pole strength, that is Q. Here, this force acts opposite to that of magnetic field, so we use a negative sign here. Clear? Now, To get the total force acting on this magnet, I need to add these two forces, Fn vector plus Fs vector. Now the total force is represented letter F vector. It is net force. Now this total force can be obtained. In the place of these two, I substitute their value. Fn vector is Qm B vector plus Fs vector is equal to minus Qm B vector. So what happened? These two get cancelled and what we obtain is nothing but 0. Here the net force acting on the bar magnet placed in uniform magnetic field is 0. So it doesn't show any kind of translatory motion. Translatory means movement in a line. Okay, doesn't show any translatory motion. Instead, this force act in this direction and this force act in this direction. So it rotates the magnet about the midpoint. Clear? This is how the bar magnet experiences a torque. Torque means the measurement of rotation. The measure of rotation is referred as torque. I hope you have understood. And here, torque, which is the measure of rotation, is represented by letter tau. Yes, it is a letter tau. It is pronounced as tau. Okay. Now let's find out the torque experienced by this bar magnet placed in uniform magnetic field. Okay. Here torque is obtained if we multiply the perpendicular distance between the magnetic poles with any one of the force. Acting on the magnet. Here, perpendicular distance is nothing but 2L sin theta. 2L sin theta. And the force acting on it, what? Qm B. Okay, Qm B. Here I have taken the magnitude of the force. Okay, if I take the magnitude of this force, if I have Fn modulus of Fn vector as a Qm B vector, and the modulus of Fs vector is a modulus of minus Qm B vector from this expression. So this will be equal to what? Qm B. Similarly, this one will be equal to Qm B. Okay, both of them have the same magnitude. This is what I have written here. Alright. The next I rearrange this one. How? In this manner. 2L Qm B sin theta. If I write it this way, it is not going to make any difference. Fine. The next thing, we know that the product of the length of the magnet with the pole strength provides us magnetic dipole moment, represented by letter Pm. So this one is equal to Pm. I write here Pm. Then we have B from the above expression in sin theta. This is a torque expression for torque experienced by this bar magnet placed in uniform magnetic field. Now we know if we have A vector in a cross product with the B vector, then this can be written as AB sin theta. Okay. In our case, we have a PM B sin theta. This can be written by following this expression as PM vector cross B vector. Okay, this I am going to use here. Then what do I get? I get this. Also, PM vector cross B vector. Okay, this side we have term. Now both have a vector symbol. So the same I use here as well. This is the final expression of torque. Okay, I box this. So, torque is nothing but the product of magnetic dipole moment and magnetic field. And here, as the magnet rotates in clockwise direction. This is the clockwise direction. The moment, the way the hands of clock moves is known as clockwise direction. I repeat, the direction in which the hands of a clock move is known as clockwise direction. So this is the clockwise direction. See, according to the diagram, these two forces will make the magnet to move in a clockwise direction. So according to corkscrew rule, now if you rotate the corkscrew, I have corkscrew in a clockwise direction, then it projects inward. You can see it projects inward. Similarly, here I place the corkscrew in this manner and I rotate in clockwise direction. Then the corkscrew move inward. So according to corkscrew rule, the torque acts inward. Clear? I hope the video is useful. If you have any kind of doubt related to the topic, kindly put your questions in the comment section. Thanks for watching.